I am Ali Amarloo, and I'm going to talk a little bit about my project in Turbulence or Turbulent Flows. And this is the title of my project, Data-Driven Runs Modeling of the Turbulent Flows. And my supervisors are Mahdi, Pourya, and Alexandros. I thought that at the beginning I better start with the idea of the turbulence, because you may know that word from when you are traveling in the plane that you heard turbulence. But when we are talking about turbulence here, generally in fluid dynamics, we are talking about high velocity flows. And I thought maybe this example is a good example, and you have probably experienced it in your kitchen, that when you have low velocity, you can see that the flow is very stable, you have constant velocities. But when you increase the velocity, you see that we are seeing a lot of fluctuations and chaotic behaviors, which we call a turbulence. But in the laminar flow, which is this one, everything is very stable. And when we look at the nature and around in the industry and everywhere, we see that mainly everything is turbulent. And we need to find a way to predict their behavior. So if you want to design something or build a new thing, we need to know the behavior of the flow. And for that purpose, as you have probably heard about it, we have a bunch of equations, governing equations, which are from the physics of the flow, and we call them Navier-Stokes, and they are partial differential equations that we would like to solve. And if we can solve these equations, we can predict the behavior of the flow. But the problem is, if we want to solve them analytical, we can't, because they are very nonlinear and complex. And we are waiting for a mathematician to help us here to solve these equations, which I think that is not going to happen soon. So in the meantime, we are going to do it numerically by discretizing the domain to smaller pieces and making some approximations and solve the equations. But the problem is here that the computers nowadays are very powerful in computation, but unfortunately they are not good enough. They cannot help us, because especially with the turbulent flows. To illustrate that, in turbulent flow, we have these fluctuations, chaotic behaviors, and we have movements, which we like to call them eddies. These eddies or movements, they can be very large or very, very, very small. And if you want to predict the whole domain, you have to make your grid sizes very small to capture those small movements and fluctuations, which makes the computation very, very expensive and almost impossible in most of the industrial and nature cases. We can do it in very simple flows, small cases, but practically not in the industrial way. So what we can do, we ask this question, that how accurate we want to be. Because if we want to solve those equations completely numerically, that we can capture all of the fluctuations, we call it direct numerical simulation, or short term DNS. We are capturing all of the things. But another solution is, let's get rid of small fluctuations and only being interested on the large movements, because they are containing most of the energy and most of the turbulence happening there. They are important. So we apply a filter and we call it large eddy simulation, because we only are talking about the large ones. Or we can go further and remove all the fluctuations and only talking about the mean values. So there is no information at the results about the fluctuations. And we can only predict the mean values of the quantities like velocity or temperature. So in that way, is the RANS, and we call that one RANS because I used that name in my title. It was called after Reynolds, so Reynolds average Navier-Stokes. But is it good? Actually, it is good, and everybody wants RANS, because first of all, the first reason is, as I said before, you don't need higher very, very high powerful computation power to numerically simulate them. So that's good. And the another reason is that in the most of the industrial cases, people, they don't care about what happens in the flow. They want to know like what happens in their system. For example, if they're simulating the flow over a car, they want to know the force that is applying on the car, or the drag friction of the air, or if they are designing a wing for a plane or a turbine, they want to know the lift for calculation of the power. They don't care if the flow is fluctuating or not. So they are happy with the runs, and they don't want to go to all the details, which is not necessarily helping. So the RANS is wanted, but there is a problem with that when we are applying this RANS method, we are separating the fluctuating flow to a mean value and the fluctuation part around that mean value. And when we apply this to our PDEs, aka Navier-Stokes, we see that we have PDEs of the mean values, but we have also terms that they are dependent on those fluctuations, and we don't know how to calculate those because we are getting rid of all the fluctuations. But they are important because in reality, they are influencing the mean flow. So we have to take account for them. But how? We have a lot of physics-based models that they are trying to guess a value for these parameters. If you have heard about K epsilon, K omega, and a lot of them, they are for this purpose, to finding that value, but they are very limited. They cannot predict for all the cases. They work for one case and they don't work for another case, and they have constants that should be tuned and these problems. So the idea is maybe we can put a computer that can learn and help us for prediction of those parameters, terms that are dependent and we don't know about them. So my project, I hope that now it's more clear, is a data-driven RANS modeling of the turbulent flow, and it's a multidisciplinary project between mechanical engineering and computer science. We have on one side mechanical engineering, fluid dynamics, turbulence, and RANS, and the other side we have computer science, data science, machine learning, and preferably deep learning for this purpose. But does it work, you may ask? So one of the first works in this area was published in 2016, and they tried this idea on a duct flow. And you can see on the right the DNS, if you remember, the first type of simulation with all the fluctuations. And they took an average of that, and they saw that, okay, we have some rolls inside the duct. And when they used the conventional physics space, and they saw that, okay, this doesn't work well, we have no movement in there. And then they used the train system, and they saw, okay, we are seeing these movements, so it's much, much better than conventional systems. But they are not still very good. They are different, at least in size or magnitude. So there is a potential for that, and we can work on it. But these problems and potentials are more than that. Like, we have to introduce the physics of the flow to the machine, because we have data, but if you remember, the problem was that we cannot perform the high simulations on all cases. So we don't have enough data. So maybe we have to use the physics of the domain to make the computer much more smart to learn faster. And that can show itself in outputs or inputs of the machine. How we are going to define that, or what is the input, what is going to be more efficient to tell the computer to learn based on that. And we have different type of machine learning methods that we can try. We can go deeper, and we can go more complex. And there is another problem that recently raised in the community was the ill conditioning of this way. We can see that here. This one was the neural network system. This one is the true DNS. What they did, they calculated those terms based on DNS, and they imported that to the RANS. And they saw that they are getting very good results, but still not the same. So it means that even if we train a computer that can perfectly works 100% accurate, we still don't receive the actual thing that we are expecting. So it's somehow ill-conditioned. And there is that problem that people are struggling with now. And we don't have a benchmark system for the systems. So almost there is no transform learning happening in this area. And also we are interested, maybe we can to some data augmentation, like the rotation of the cat picture. Maybe we can do something equivalent to that in the fluid dynamics way, so we can have a better machine to learn. And the physics of interest in our group is mainly atmospheric flow, which is very applicable for the industry here with the wind farms and wind turbines. So at the starting point, we are trying to see if we can use this neural network well trained to predict the RANS simulation of this type of flow. And in the next steps, we can go further for generalizing to other physics and other geometries. And let's hope to find good results in that area. So that was it. Thanks for your attention.